Hello, it's Mr. Quaddy here. Today we're going to be going over the inverse normal distribution. Inverse normal distribution allows us to work backwards. So, for example, if Z is a standard normal distribution, find K such that the probability that Z is less than K is 0.81. So there's a standard normal distribution here that looks like this, and there's some sort of cutoff K. We don't know the cutoff this time. However, I do know that this area is 0.801 or 80%. And this is a standard normal distribution. So we say Z belongs to, or has the parameters 0 and 1. Okay, so to do this, I would go into my calculator. I'm in a calculator window. And so if I want to do the inverse normal, as always, I press menu. And then I go down to statistics and I choose distributions. Now this distribution is the inverse normal distribution, so hopefully you can click the right one. It asks us for the parameters. Well, we know the area is 0.801. This is a standard normal distribution, so there's the information. I press OK, and there's my answer, 0.845. And so we get this answer, K is equal to approximately 0.845. We call that the cutoff, or the quartile. And so there's the instruction of how it works on a calculator. You press menu, statistics, distribution, inverse normal, and then this is the very important, the area below the cutoff. This is mu and this is sigma. Okay, let's do another question. If P is a standard normal distribution, find K that the cutoff such that Z is greater than the cutoff is equal to 0.73. So if I were to draw this probability distribution, it looks something like this. It's not a very good one. And okay, so we need the probability to be greater than some cutoff, and it's over 50%. So my cutoff has to be here, because we're talking about everything to the right, everything greater. This is going to be 73%. Now, our calculator can't do this because, remember, when you type it into the calculator, you can only put the area below the cutoff. So we need to know what this area is. So as you can imagine, we're going to redraw this, or reconsider it. This is the same cutoff, K, but now I'm looking at this area. This is 1 minus 0.73, which is 0.27. So let's just put a little note there. We need the area below the cutoff. So what I would write is the probability that Z is greater than K is 73%. Well, if I rewrite that, I have the probability that Z is less than K, that is equal to 27%. And then using my GDC, okay, for this one, same as before, I press menu, statistics, distributions, inverse normal. And then I'm going to put in an area. This time the area is 0.27, and it's still standard normal, so I press OK, and it spits out my answer, negative 0.613. So a reminder that when you use the inverse normal, you need the area below the cutoff always, and the mean and the standard deviation. We find that K is equal to negative 0.613. Notice how the answer here, what you're given, 0.73, doesn't have anything to do with the answer to the question. You have to use your GDC correctly to get the answer. And it makes sense, right? The cutoff is negative 0.613 because it's to the left of the axis here. Okay, let's do a question with real numbers. A university professor determines that no more than 70% of the year's history candidates should pass the final exam. The exam results were approximately normally distributed with a mean of 62 and standard deviation of 13. Okay, so we're gonna draw this. This is our normal distribution. This is really mean to for the professor to do. They know the mean of the the mean is 62. In fact, we should label this. This is x is a random variable following a normal distribution with a mean of 62 and a standard deviation of 13. We write squared there. Okay, so, and we know that we want to find the lowest score to pass. How many pass? 70%. So this is 50%. So there's some cutoff here, and everyone above passes. So let's color that in. Okay, so this is 70%. Now, we want to find the lowest, we want to find what this cutoff is. Well, again, I can't just type this into my calculator because my calculator only helps me find cutoffs if I know the area below. So I need to do a little bit of thinking here to figure out what the area here is. This is the complement. 1 minus 0.7 is equal to 0.3. And now I can punch this into my calculator. Just to rewrite what I did, so the probability that x is greater than k, this is 0.7. Then I rewrote this, the probability that x is less than k is 0.3. These two statements are the same. And now using my GDC, I have my area, I have my mean and my standard, my normal distribution, sorry, my standard deviation. I type that in. So I go menu, what do I do? Statistics, distribution, inverse normal, and then I'm going to type in the area. For this one, the area is 0.3. For this one, we have a different mean. The mean is 62, and the standard deviation is 13. Press enter twice, and there's my answer, 55.2, basically. Find that k is equal to about 55.2%. So that's my cutoff. In other words, if you get 55% or higher, you pass the course, because the professor is determining the number of, they want to know how many people pass, so they just choose the passing grade based on this number, which is a little unfair. But this is how our IB program works as well, right? Every year they want to only ensure that top 5% get a level 7, so they look at all the IB people in the world and they count down the top 5%, and then they find the cutoff for getting a level 7. Okay, let's do another question. So we have a normally distributed function, and we want to find a such that the area that we're between these two values is 0.42. Okay, so let's draw my standard normal distribution. Okay, well, we know this is x belongs to n 23 5 squared. Perfect. And okay, so we know the center value at least, it's 23. And then we know that x is between 23 minus a. So I don't know what a is, but I know 23 minus a would be here. And it's not, it should be a better drawing. 23 plus a is here. And I know that this area then between the two, this area is 0.427. So I've been given an area, so I need to work backwards to find my cutoff. So this is an example of the inverse normal function on my calculator. The question is, I need to know the area below. So I could look at this cutoff and look at the area below. I don't really know what this area is. I'm kind of not doing great. However, I could probably figure it out because of the symmetry of the normal distribution. If this is 42%, then these two areas, which should be the same, my drawing isn't great, they should be about 68% combined, and then, or sorry, 58% combined, and then I would split that in half because they're symmetrical. So I should be able to figure out what this area is. Let's write that over here. The non-shaded area is 1 minus 0.427. That's the complement. That gives me 0.573, right? That's the complement.
Okay, and now the lower shaded area, unshaded, is that number 0.573 divided by 2, which gives me 0.2865, and that's due to symmetry. So now this area here is 0.573 divided by 2. So now the probability that x is less than that number 0.2865. So I know the probability that x is less than this cutoff, 23 minus a is the cutoff, is 28%. So if I know a percentage, I know the area, we have to work backwards using the inverse normal function. I typed that into my calculator.
Okay, for this one, we're going to type in menu, statistics, distributions, and we're going to go to inverse normal. The area this time was 0.573 divided by 2, which is 0.2865. The mean was 23, and the standard deviation was 5. Press enter twice, and my cutoff is 20.18. That's not the answer to my question. As you'll see, we have to do a little bit more math with this number.
And I find that the cutoff from my calculator is 20.18. So look at how we did it. This what we just found. We usually, when we get our calculator result, it's just k is equal to the result. But in this case, it wasn't. The cutoff isn't called k. The cutoff is called 23 minus a is equal to 20.1818. Now to solve for a, well, I have to I have to do some algebra. Subtract 23 from both sides, and I end up with 2.82 as my answer. So this was actually around 21, and this was around 26, or sorry, 25, and that's where 42% of my data lives. So just be careful when you do use the calculator to find the inverse normal. So using GDC, just be careful that you always set whatever was here. If it was a k, sure, but if it's some other expression, you set that equal to the number that comes out of your calculator. Okay, let's turn the page. Okay, now these are special types of questions that you're going to see in your homework, but these are questions where we have an unknown mean or an unknown standard deviation. And this is where we're going to have to use that standard normal distribution. Remember when we talked about the standard normal distribution, we taught you the z-scores. It's like, why are we doing this? We don't really need it anymore. Well, unfortunately, we do need it to solve questions like this, where you don't know these two parameters. For example, we have an adult scallop population, and they have a normal distribution. Standard deviation is 5.9. 15% of scallops weigh less than some amount. So I'm going to draw my normal distribution. We don't know the mean, right? That's our unknown. But we know this follows a normal distribution with an unknown mean, we'll call it mu, and a standard deviation of 5.9. I have to write squared. We also know that there's a cutoff, 15% of scallops weigh less than 58. Well, that means a small amount, so my cutoff has to be somewhere here. And this area, this is 15%. Okay. Now, I need to find the mean. So if I were to go to use my inverse normal, because I know the area, if I use the inverse normal function on my calculator, I'm gonna have a problem because I know the area, but I don't know the mean, so I can't type it in. The way we're gonna solve this, we're gonna write a little note here, so we'll put a big arrow. We cannot solve as such because mu is unknown. Therefore, transform to z. We're going to redraw this normal normal distribution as a standard normal distribution. Remember, standard normal distribution is the one that's centered on the axis. We know the mean is 0. We know the standard deviation is 1. That's always given. We know that we're talking about a cutoff, and we know that this is an area of 15%. So the question is, what is this cutoff? Before it was 58. Well, it just so happens we have a formula to do that. We have the z-score formula. The z-score is the original value minus the mean divided by sigma. So my original value was 58.2, mean I don't know, and the standard deviation is 5.9. So notice how I was able to draw this over here. A few things changed, but the big one that I had to calculate, the only one I really had to calculate, was the z-score. And as you can see, I didn't really get a full answer. However, look how the questions changed now. Before, we knew the probability that x was less than 58.2. We knew that was equal to 15%. Now, once I've done the transformation, we know the probability that z is less than, okay, here before it was 58, now z is less than this awkward number, 58.2 minus mu over 5.9. And that's equal to 15%. Well, now we're talking, because now I can use the inverse normal distribution on my function, or on my function on my calculator. I know the area, I know the mean, I know sigma. So I'm going to go type all these into my calculator.
For this one now, we're going to do the same thing we've always been doing. So menu, statistics, distribution, inverse normal. I'm going to type the area, which is 0.15. This is a standard normal distribution, so I press OK, and I get negative 1.03643. Again, we're not done. This is just the cutoff, but now I can go back and do some more math.
Then my calculator spits out this cutoff of negative 1.03643. That's the cutoff. So that's this amount. Again, it's not called K this time, it's called 58.2 minus mu. So it's 58.2 minus mu over 5.9. That's confusing, but really this is easy solving now because I just have to isolate for mu. So I'm going to cross multiply, so I get 58.2 minus mu is equal to negative 6.11496. That's with my calculator. And then I'm just going to solve for mu. Just go up here, run out of space. Mu is equal to, mu is equal to, if you solve for this, eventually you're going to get 64.3 grams. So that is the average weight of the scallop. And of course, that would make sense, right? Because 58.2 is the low cutoff. So there's a few steps here. One was transforming the whole thing into the Z domain, finding the Z score, then using the inverse normal in your GDC, but then you do have to solve at the very end. So this is this step to this step, I see constant confusion among students. Once you found the number in your GDC, you're not done. You still have to solve for the unknown. And we can get some really tricky questions. This last question, we want to find the mean and the standard deviation. We don't know either of those two things. So the first thing we know is that for this normal distribution where we don't know the mean or the standard deviation, so we're going to call it x normal mu sigma squared. But we do know that x is less than the cutoff of 20, that's 0.1%, so that's a small amount. So some small amount, 10%. And that cutoff is 20. The central value is mu, we don't know. And then the fact that when x is greater than 29, it's also a pretty small value, it's 15%. Okay, so we have these two pieces of information. Again, I cannot type anything into my calculator because I don't know what the parameters are. But if I transform it into a standard normal distribution, so I'm going to go like this. And this is again a cutoff, it's still 10%, but the z-score, we'll call it z1 because we're going to be doing two of these, is 20, the original value, minus mu over sigma. Similarly, if this is 15% here, this is also z-score 29 minus mu over sigma, those unknown things. And this, of course, is z, follows a normal distribution of 0, 1. Now let's look at this one first. So let's look at this cutoff. We should be able to solve it. Probability that x is less than 20, well, that was 0.1. The probability that you're below this cutoff is 0.1. We can't solve this, but we can rewrite it. The probability that z is less than 20 minus mu over sigma, that's 0.1. So now I've written it with this. The probability that I'm less than this cutoff is 0.1. Now, using my GDC.
Okay, you guys should be pros now at this point to put in the inverse normal. So I go inverse normal. The area for the first one is 0.1. We don't know anything else. Okay, so I press OK. So there's my cutoff. It's negative 1.28155. Again, that's not everything. I'm going to put that back into my equation.
I find that if I were to type this into my GDC, I get negative 1.28155. And this is 20 minus mu over sigma, because that's my cutoff. Now I can cross multiply. I get 20 minus mu equals negative 1.28155 sigma. I know you're going to be sad because there's two unknowns there. We can't solve an equation with two unknowns. So let's look at this other piece of information I have. I know that the probability that x is greater than 29 is equal to 0.15. Again, I can't use that, so let me rewrite it with in my standard normal distribution. Again, the area greater than this cutoff is 0.15. Again, I can't solve this with my calculator because I can't look at a tail that's greater than a cutoff. I have to look less than a cutoff. So I have to use the complement. So that's less than 85%. That's the complement. Now, typing this into my calculator, there's my area, and there's my mu and sigma.
And for the last one, we go menu, statistics, distributions, inverse normal. And I'm going to type in the area, which is 0.85. Remember, it's the complement. Still standard normal distribution. Press OK, and I get 1.03643. Again, that's the cutoff, but I'm going to put that into the math.
And it tells me the cutoff is 1.03643. Again, it's equal to this number here, the thing that was in my bracket. And if I cross multiply, again, I get an equation that has two unknowns. Now this isn't great, except we taught you a long time ago how to solve things like this. This is a system of equations where you have two equations and two unknowns. So you should be able to solve this system. You can use substitution, you can use elimination, all those things you learned in grade 9 and 10. Of course, you have the GDC, so you should just be using the GDC.
Okay, and for solving linear systems, you can do it by hand, but it's a lot easier to use your GDC. You press menu, and this is an algebra thing we're doing, so we go to algebra, and there, solve linear system of equations. So now, how many equations are there? Well, there are two. Those are the two variables, x and y, so make sure when you type them in, you're using x and y instead of mu and sigma. And then I press OK, and it says, okay, well, can you put in your two equations? Oh, I gladly will. So I have 20 minus x equals negative 1.28155y. And then down here, I have 29 minus x is equal to 1.03643y. I just press enter. The calculator is just going to do a linear solve. And there it spits out x, it's 24.9759, and y is 3.88269.
So we type these values into the GDC and it spits out our answers, which are mu is equal to 24.9759 and sigma is equal to 3.88269. Therefore, mu is equal to 25.0, sigma is equal to 3.88. Okay, and that's definitely the most complicated question you could have, where you have to find two equations. Hope that helped you understand inverse normal distributions. Here's some homework for you, page 546, number 1 to 4, 548, number 1 to 5, 550, number 1 to 11. All right, enjoy, and until next time.